Welcome back, everyone. In this lecture, we introduce inverse functions and graphs. Let's begin with a general idea of an inverse function. If you remember the basic definition of function from previous lectures, a function is a rule which assigns to each element x from a set A exactly one element y or f of x and another set B. Now, inverse function will do the opposite. Inverse of the function f will take y from the set B as input and go back to x as output from the set A. Now, of course, we can't do this for all functions. If you look at this example, a function where 1 is assigned to 2, 4 also assigned to 2. If I try to inverse this function, I try to go back, what you notice right away is that for the input 2, there will be two different outputs, 1 and 4, and that's not a function. So clearly, not all functions have inverse. Which ones do? Only one-to-one functions. So let's take a look at the definition of a one-to-one function. A one-to-one function is a function where not only for each x there is exactly one y, but also for each y there is exactly one x. We call that a one-to-one function. In other words, no two input in the domain have the same output. So clearly, this is not one-to-one. Let's take a look at an example. Is f of x equals x squared a one-to-one function? Can we think of two different input which gives the same output? Yes. F of 2 is 4. F of negative 2 is also 4. F of 2 equals f of negative 2. For two different inputs, 2 and negative 2, the output is the same. F is not one-to-one. We could also decide using graph of a function whether the given function is one-to-one or not. How? The definition of one-to-one function is that for each y output, there must be exactly one x input. Means that for each y coordinate on the graph of the function, there must be at most one corresponding x coordinate, no more. So if I see a y coordinate which corresponds to two different x coordinates, then that is not a one-to-one function. We call this test the horizontal line test. That if you consider any horizontal line would intersect the graph at most at one point, then it will be one-to-one. Let's apply the horizontal line test to the graph of a piecewise defined function. In this example, f of x is 2x plus 1 if x is greater than or equal to 0, negative x minus 3 if x is less than 0. We would like to sketch the graph of this piecewise defined function. So if x is greater than or equal to 0, we are using 2x plus 1. I could use 2 points in order to sketch the graph of this line 2x plus 1. I need to choose the x values in a way which are greater than or equal to 0. So how about 0? 2 times 0 plus 1 is 1. How about 1? 2 times 1 plus 1 is 3. So I will use these 2 points, 0 and 1, 1 and 3, and I get the line 2x plus 1 for x values greater than or equal to 0. Now, if x is less than 0, we're using the line negative x minus 3. Again, I need 2 points in order to sketch the graph of this line. How about I try some negative values? Negative 1. That would be negative 1 minus 3. That's negative 2. And I could also try negative 2. Negative 2 minus 3. Negative 1. So I have the point negative 1 and negative 2. Negative 2 and negative 1. Now, when you sketch this part of the graph of the piecewise defined function, keep in mind that this includes all x which are less than 0. So you need to consider all the real numbers which are less than 0. Is this a function? Yes, it passes the vertical line test. Now the question is this a one-to-one function or not? So we apply the horizontal line test. Can we find a horizontal line which would intersect the graph of this function at more than one point? Yes. Here is a horizontal line which intersect the graph at 2 different points. Means that I could find a y coordinate here which corresponds to 2 different x coordinates, and therefore this function is not one-to-one. Why not? It fails the horizontal line test. Now we are ready to look at a more formal definition for the inverse function. So the condition is that f, the original function, needs to be one-to-one. Once the condition is met, then we can define inverse of a function in this way. That if f is a one-to-one function where assigns x to y, f of x equals y, then the inverse function f inverse will be defined in a way that would take y as input and the corresponding output will be x. So f inverse of y will be equal to x if and only if f of x is equal to y. How would we find a formula for the inverse function? So we begin with the equation f of x equals y, and we solve that equation for x in terms of y. I'll show you a couple of examples from this table. For example, if y is equal to 2x, then I solve this equation for x, and x becomes equal to y divided by 2. If y is equal to 3x plus 1, then 3x is equal to y minus 1. X is equal to 1/3 times y minus 1. If y is equal to x cubed, then x is equal to cube root of y. These are just a few examples on how we solve an equation for x in terms of y. Let's give this a try. F of x equals x minus 3 divided by x minus 4. Find a formula for F inverse. So I'll begin with y equals x minus 3 divided by x minus 4 and solve this for x. So y times x minus 4 equals x minus 3. That is xy minus 4y equals x minus 3. We're solving for x, so let's move all x's to one side. Xy minus x equals 4y minus 3. And let's factor out x. So x times y minus 1 equals 4y minus 3. And so x is equal to 4y minus 3 divided by y minus 1. What I have here is x presented in terms of y. What I have here is a formula for the inverse function in terms of y. I could present this as F inverse in terms of y, F inverse of y. Let's take a look at the properties of inverse functions. So we define inverse function in a way that if f of x equals y, and f is a one-to-one function, then f inverse of y equals x. Now if you consider the set of all x's here, that would form the domain of f. And if you consider the set of all y, that would form the range of f. Now let's think about f inverse. Y is an input for f inverse. So the set of all y's here is the set of all inputs for f inverse. That will form the domain of f inverse. And if you put together the set of all x's, x is an output for f inverse. So the set of all outputs for f inverse will form the range of f inverse. So the domain of f equals the range of f inverse, and the range of f equals the domain of f inverse. We would also like to look at composition of f and f inverse in different orders. So let's begin with, again, f being a one-to-one function where f of x is equal to y, and therefore f inverse of y will be equal to x. Now if I consider f of f inverse of y, let's think about f of f inverse of y. F inverse of y, according to this sketch that I have here, equals x. So I will replace f inverse of y with x. Now f of x equals y. So f of f inverse of y equals y. Think about this. You're applying two functions which are inverse, one after the other. In an informal way, you could say that they undo one another. Informally, you could say they cancel one another, and you get y. In a different order, f inverse of f of x. You start with f of x, f of x equals y, so I will replace f of x with y. And next I'm looking at f inverse of y, and f inverse of y equals x. So f inverse of f of x equals x, and f of f inverse of y equals y. This is called the inverse property. It will be helpful once we get to exponential and logarithmic functions and we apply this property, and we find some very helpful logarithmic and exponential properties. Let's take a look at this example. Suppose f of x is x minus 3 divided by x minus 4, which is basically the same function as we looked at in the previous example. We would like to find the domain and the range of f inverse. Thinking about the range of f inverse, range of f inverse is equal to domain of f. So all I need to do is think about the domain of this function. Where is it defined? It's defined for everything but 4. So domain of f is all real numbers excluding 4. And that forms also the range of f inverse. Now what about the domain of f inverse? To determine the domain of f inverse, I need to actually think about the formula that we found in the previous example for f inverse. We found that f inverse of y equals 4y minus 3 divided by y minus 1. Domain of this function would be all real numbers excluding 1. All real numbers except 1. Next, we'll look at the graph of inverse function. If you consider the fact that if f of x equals y, and f inverse of y equals x. So if I have a point on the graph of f in the form of x and y, if I consider this as a point on the graph of f, then I can conclude that the point y and x, where the input and output are switched, is going to be a point on a graph of f inverse. Now when you think about the relationship between these 2 points, the point with coordinates x and y and the point with coordinates y and x, these 2 points are the reflection of one another in the line y equals x. What does that mean? Means that the point y and x is the reflection of the point x and y in the line y equals x. If you consider a perpendicular line from the point x and y to the line y equals x, and if you continue on the other side the same distance, you get the image, the reflection, which will have the coordinates y and x, where the x coordinate and y coordinate are switched. If you apply this idea to every single point on the graph of f and you find the reflection in the line y equals x, you will get the graph of f inverse. So we can sketch the graph of inverse function by reflecting the graph of f in the line y equals x. Let's practice that. The graph of f is given. Part A, we would like to find f inverse of 1. So if f inverse of 1 is equal to, say, x, then that means f of x is equal to 1. Means I'm looking for a point on the graph of f where the y coordinate is 1, where f of x is 1. What is the x coordinate? 0. So x is 0, meaning f inverse of 1 equals 0. Sketch the graph of f inverse. As we mentioned, in order to sketch the graph of f inverse, we need to reflect it in the line y equals x. To do so, we could begin with some points. For example, this point has coordinates 0 and 1. You reflect it, switch x and y, you get the point 1 and 0. Use another point, this point. It looks like it has coordinates 1 and 3. Switch, reflect it, you get coordinates 3 and 1. You could apply this idea in order to reflect that piece of the graph. Let's use more points. How about this point? Negative 1 and negative 1. Switch x and y. It is still negative 1 and negative 1. And reflect, and reflect this part of the graph with respect to the line y equals x. This graph is the graph of f inverse. We got that by reflecting the graph of f in the line y equals x. We also need to be familiar with the basic definition of an increasing and decreasing function. You will revisit this topic in Calculus 1, where you apply the first derivative of a function in order to determine the intervals of increase or decrease for a given function. But for now, we just need to know what it means when we say a function is increasing on an interval. So let's say a function f is called increasing if for two given x values a and b, where a is less than b, f of a will be less than f of b. This basically guarantees that as you increase the x value, that f of x will also increase, which will make this function an increasing function. In a similar way, we define a decreasing function, that if you choose two different x values, a and b, where again a is less than b, this time f of a is greater than f of b. This will guarantee that as you increase the x values, that the value of f, or the y value, will get smaller and smaller and smaller. So it will be a decreasing function. You will revisit the idea of increasing, decreasing function in Calculus 1, but for the time being, just the basic introduction will be sufficient. Use the textbook exercises and the homework questions to practice. This is the end of our lecture. This is the end of this chapter.